gotta laugh at yourself sometimes. Okay, so I can't remember which one we did where we used integration by parts twice before. So let me see if I can find. Well, we're not going to do that one because we've already done it. So we'll what we'll do is we'll change that, and instead of doing that, we'll do, let's say that. So remember, what you do is you use integration by parts one time, and the second integral you will have, it will simplify it, but it won't be simplified enough that you can just do the integral directly. It won't be one that's in the table, so you'll have to use integration by parts again. And typically what I do is I'll do that integration separately on a separate piece of paper, and they'll just, or separate part of my paper, and then I'll plug it back in. And also I put the 3x in here. The derivative of e to the 3x is 3x, but also the integral of e to the 3x is 1/3 e to the 3x. My daughter, she's 36 or something like that, and one of her jobs is to hire interns for the summer. And she gets a lot of people, students your age, that come and get interviewed. And talking to her sometimes, I think she does get people like that. Sometimes. It drives her crazy. There was some guy who was consistently late for work, and he would say something like, well, the train gets delayed, and so it's not my fault. And Jennifer's like, you should take the earlier train. You can't just come in late because because the train's late. If it was the first train, yeah, maybe, but anyway, she's funny about that. She also had the boss, the big guy in the company, sometimes recommends students as interns, usually friends of his, and she's got like a junior in high school that's doing an internship, or wants to do an internship, and she was saying how good he was. He was telling me about all the things he do. He's really nerdy. He says he was talking about doing the Arduino stuff, doing Arduinos. Seems awful familiar. Did we do this one or not? Okay. Oh, we just did it one time, not twice. Okay. trying to make it so you don't just copy down. I'm giving you enough help that you can hopefully continue on here. Okay. Okay, I think that's right. I could multiply this out if I wanted to, but I'm just going to leave it as such. So all we did was we got to this point, instead of having x squared e to the 3x, we just have x e to the 3x. So I go ahead and put that over there separately. Choose u as x, dv is e to the 3x dx, and go through the whole thing. We did one similar to this with e to the 2x, I think, x e to the 2x. So once you've got this done, then you can substitute it in here. So you don't forget your constant that you had earlier. That was from 2x, 2 there, from 3 there. It gives you 2/3. And there I have plus c. I just ended up plus c on the end. I didn't take 2/3, negative 2/3 c, because negative 2/3 c is just an arbitrary constant. Okay. So did I assign the homework from this section or not? I think I did, didn't I? So we're going to move on to the next section. Okay, so we've actually done some of this already. It's just some more complicated versions of integrals that involve trig functions. Most of the time it ends up being polynomial integration. So it's a use substitution kind of situation. Let's just, I'll give you some examples of problems that we've probably already done and what the substitution would be. And in reality, this is not as important as the next section, but to do the next section, you've got to know how to do this stuff. So that's kind of, you'll see this within trig substitution more so than you'll see it by itself. So, for example, back in chapter 4, we asked what is the integral of the tangent of x dx? And what we did is we substituted the definition of the tangent as the sine over the cosine. And then we let u equal the cosine of x. And du, therefore, is going to be negative sine x dx. So the derivative of the cosine is negative the sine. And so when you do that, when you make that substitution, you'll have 1 over u times negative du. And then you integrate that, you get negative the natural log of the absolute value of u plus c, and that's negative the natural log of the absolute value of the cosine of x plus c. Okay, so we did that. We probably have seen something that looks like this. If you had the sine cubed of x times the cosine of x dx. So again, if you let u equal the sine of x, du will equal cosine of x dx. So this part is du, and this part is u. So you end up with the integral of u cubed du. And so it's just a polynomial integration. So you get u to the 4th over 4 plus c, and then you plug u back in. So you get the sine to the 4th of x over 4 plus c. So I think we've done something similar to those kinds of things. I know we've done that because we did it just the other day when I couldn't remember what the integral of the tangent was. So the second one, though, it's made up of both the sine and the cosine, and you realize, oh, the sine is derivative of the sine's the cosine. And what I did here was, the sine cubed of x is the sine of x cubed. I skipped that step. So, right here, really, this is the sine of x quantity cubed. So if you make that substitution, that's how you get u cubed. And I always tend to write this in this way before I integrate so that I know that's what I'm really doing. Sometimes people kind of forget what that means. With the exponent between the sine and the x is the sine of x cubed. Okay, so those are trig integrations that we've done before. What we're going to do is we're going to solve kind of the technique for solving the general form of the sine of x to the m power times the cosine of x to the n power, and the sine of the secant to the m power of x tangent of x to the n power. And remember what I said is, what that means is the sine of x quantity to the m and the cosine of x to the n. And so ultimately we want to get into a form kind of like this, where this part of the integral is in terms of one trig function, and we have at least, well, we have the derivative of this, the sine here is the dx, the du part. So if this were cosine cubed x and this were sine x, then it would work out as well too. But they're not always initially in this form where you have one part that's one trig function and the other part is clearly the other part of the trig function. Sometimes you can just, you can see it's similar enough to this. If I had sine to the 5th x cosine x, then that'd be easy. Same substitution. But it depends upon the exponents, whether they're even or odd, or both even or both odd, um, the sine integrals tend to be easier. And what you do is you use these trig identities a lot of times to rewrite the product such that it ends up looking something like this. So we use the Pythagorean identity and the power identity for both the cosine and the sine. So those three trig identities we'll use a lot. More so the first one than the second two, but so let's look at a problem, I think, here. Well, yeah. So here's the strategy. You either let sine of x be du, sine of x dx be du, or the cosine of x dx be du. Convert the remaining terms to either cosine or sine, respectively. So if you choose du as the sine of x, you want to convert everything else to the cosine of x. If you choose cosine of x dx as du, you want to change everything else to the sine of x. So this example that we did here, we chose cosine of x dx to be du, and everything was already the sine. But it doesn't always end up being that way. Sometimes it's not always all that way. So I'm going to make one up here. So let's say we have the integral of the sine cubed of x times the cosine squared of x dx. So now I've got both the sine and the cosine raised to a power. So it's not. So I can either. There's two options here. Option one is I can choose du to be cosine x dx. So by just taking one of these cosines and separating it, so this part would be du. Or I could take one of the sines, so so if I take one of these sines and make it du, so I have the sine of x dx being du, I get sine squared x cosine squared x. So they're both the same. I haven't done anything different. I've just separated them apart. Now, because if I didn't have this part, I'd be in good shape. This would be u would be cosine of x, and du would be negative sine of x dx. But I've got this thing. So in this case, only one way works. One way, I guess, only one way works. And the key thing is that if you go back and look at these trig identities that I pointed out, these involve squares. So you can only use the Pythagorean identity when you have a square of something. And what I want to do in the second line is I want to convert everything that's not du into sine of x. So I want to convert cosine of x into the sine of x. Well, there's no Pythagorean identity that works for that. Whereas down here, where I choose du as the sine of x dx, and I want everything else to be the cosine, it already is the cosine, I need to convert this to cosine. And I can do that using the Pythagorean identity. So it's the second one that's the correct choice. So what I have is, so the Pythagorean identity says sine squared x plus cosine squared x equals 1. And therefore I can solve for the sine of x, the sine squared of x. It's equal to 1 minus the cosine squared of x. So then I make that substitution into here. So instead of sine squared x, I put in 1 minus cosine squared x. So you get 1 minus cosine squared x times cosine squared x times sine x dx. So now I have converted it. So everything that's not du is, in this case, du is sine x dx. So I'll just multiply that out. So just distribute that to both terms in the parentheses. that. And now I can use, so my u substitution will be u is the cosine of x, du is equal to negative sine x dx, or sine x dx equals negative du. So the integral from this form becomes u squared minus u to the fourth times negative du. And so my original trig integration ends up just being a polynomial integration. So when you integrate that, you'll get negative u cubed over 3, so you get the negative sign here, and minus u to the fifth over 5 plus c. And then we go back and substitute back in, so we've done our integration with respect to u, but we want the equation in terms of c, so that's going to be cosine of x cubed over 3 minus cosine of x to the fifth over 5 plus c, and in the shorthand notation, it's cosine cubed of x, cosine to the fifth of x plus 5c. Okay. Okay, so that's the basic idea. And it all depends on, which method you use. I don't like the way the book does it, because they kind of say if m is if one is odd and one is even, then you do this, and if one's they got all these rules. But the reality is, you've just got to realize, going back to our original choice here, that of the two choices we have, one ends up where we have a something squared, which we can convert using the Pythagorean identity. The other one is not squared. So that's kind of the trick, is to figure out how to rearrange these things so that you can use the Pythagorean identity. Now, I just told you not to use the rules, but I'm going to tell you the rules just to show you why. But then when we actually do them, I'm not going to use the rules. So if you let's say you have the sine of m to the sine of x to the n power cosine of x to the n power dx. Okay, so if m is odd, use du equals the cosine of x. Did I write? No, that's not the one I want to use. Use a sine. Okay, so that was our example here. Because the exponent on the sine was odd, I can take one of those, the one that causes it to be odd, and move it over here with dx and make that du. And then I can use the Pythagorean identity on the squared term here to then substitute for this something in terms of the cosine. So that works out. It turns out if n is odd, use du equals the cosine of x dx for the same reason. Because if you have an odd exponent on the cosine, you can take one of those away, it becomes even, and then you can use the Pythagorean identity, solve for the cosine squared of x. And do it. If m or, let's say m and n are odd, use either. Doesn't matter. So if you have, and that, what am I talking about there? I'm talking about if you had the integral of the cosine cube of x sine cubed of x dx. You can use either one of them. You can either use du as being sine x, because that'll change the sine cubed into sine squared, and then you can use the Pythagorean identity to change the sine squared into cosine squared, or you could do the other way around. It doesn't matter. So if m is odd, but I didn't say but n is even, but that's kind of what I'm saying. If n, this is the case, if n is odd but m is even. If they're both odd, then you can do it either way. So then the question is, what do you do if they're both even? So let's say, the question is, what is the rule if m and n are both even? So that would be this example. If you had the cosine squared of x sine squared of x dx. And you're like, well, I could use the Pythagorean identity for either one, but that's not going to work. Well, let's see if it doesn't, why it doesn't work. Maybe it does work. I don't know. Let's try it. Let's just try it. So if I, because if I take one of these and I match it up with the dx, I'm going to be in the same situation that was back here, where I can't convert that remaining cosine or sine into the other trig function unless it's squared. I can't use the Pythagorean identity. But you might think, well, what if I did change sine squared to 1 minus cosine squared, like that? So that would give me the integral of the cosine to the fourth of x dx minus the integral of the cosine squared of x dx. They're still even. And I can't, if I take a cosine here and match it with the dx, I've got cosine cubed, which I can't do anything with because it's odd. So that doesn't work. That's not going to work. Well, the answer is this. So if they're both even, then you have to use one of these power reducing formulas. So let's just do that for that particular example. And you actually you'd have to use both of these. You can't just use one, because then you'd have arguments that are with different coefficients in front of the cosines and the sines. It's not going to work out. So let me just insert the one I was just working on here. So what the question was, what's the integral of the cosine squared of x times the sine squared of x dx? So for cosine squared, I would put in 1 plus cosine 2x over 2. And for the sine squared, I'd put in 1 minus cosine 2x over 2. And if I multiply this out, I'm going to go ahead and factor out the quarter, a half times a half, and then I'll have 1 minus cosine 2x times 1 plus 2 cosine 2x. So if I multiply that, I'll get 1 squared. The inner and outer cancel out, and I get plus or minus the product of those two, which is I'll get negative cosine squared of 2x times dx, which is just 1/4 the integral of 1 minus cosine squared 2x times dx. So that's equivalent. We haven't done, all we've done is algebra and trig identities. The problem we have is that now we've still got cosine squared. We've still got a cosine squared here, which is still a problem. But then what you do is you use this formula again, and instead of the argument being x, it's 2x. So then we use for the second part of this integral, we substitute in this again, so we get 1 plus cosine of 4x divided by 2, the whole thing times dx. And you've got 1 minus a half, so we'll have 1/4. So we'll have the integral of 1/2 minus the cosine of 4x, whole thing times dx. So the integral of the first part is just 1/2 x. And the integral of the second part is going to be 1/4 the sine of 4x. There's your answer. Almost. I haven't multiplied everything out yet, but so here all we have is the integral of 1/2 dx, which is just the integral of dx, which is x. And here it's just like when we were integrating e to the 3x, we divided by 3. So here we have the cosine of 4x, so we divide by 4. That's just use substitution, but we're going to skip that because it should be easy to do. We don't need to do that. And as far as the sine is concerned, the integral of the cosine is the sine. So this stays negative. If it was the sine of 4x, the integral would be negative the cosine of 1/4 to negative the cosine of negative 1/4 cosine of 4x. The integral of the cosine is the sine. The integral of the sine is negative the cosine. So in review here, when you have an odd exponent on the sine and an even exponent on the cosine, you choose du to be sine of x dx. That's what we chose right down here. If the exponent on the sine is even and the exponent on the cosine is odd, then you choose du to be cosine of x dx. If they're both odd, you can do either way. And if they're both even, you have to use the power reducing trig identity more than one time, or unless your original integral was just the cosine squared of x, then you don't have to use it one time. But because in this case I had cosine squared x times the sine squared x, when I did the original application of the power reducing formula and multiplied it out, I still had an even exponent, which meant that I had to use the power reducing formula one more time. So those are the 4 cases. So let me just give you one here to think about. I'm just going to So if I said, what's the integral of the sine to the 7th of x times the cosine squared of x dx? So you're going to have to choose. In this case, you choose du first. And u is going to be, the integral. Whatever this is, you take that, the integral will give you u, or you can choose u and calculate du. It doesn't matter. But remember what you're going to do is the rule was if the exponent on the sine was odd, then you make du equal to the sine of x dx. If the exponent on the cosine is odd, then you choose du to be cosine of x dx. So once you've done that, first thing you want to do is to rewrite this in terms of either the sine of x dx is du. Take one of these things and put it separately and see what you have left, and then use the Pythagorean identity to rewrite it. I'd wait to do the substitution once you've used the Pythagorean identity. So I'll give you a minute to think about what du should be. Hopefully you've already figured it out. You can look back at the previous examples that we've done if you want to. And actually, let's not carry out the integration. Let's just set it up. We'll get the u substitution in there, and then you'll see why I say that in a second. And anytime you have something like sine squared x cubed, then you multiply the exponents together. So the sine of x to the sixth power is the sine squared of x to the third power. So that's as far as I'm going to go with this one. I mean, it's not, you just have a third order thing you got to multiply out, but we're not going to do that today. So what I've done is, because sine was to the odd power, I chose du to involve the sine of x dx. So that meant u had to be the cosine of x dx. The derivative of the cosine is negative the sine, so I put that negative sign in there. Then I said the sine of x to the sixth power is the sine of x to the second power raised to the third power. Then I used the Pythagorean identity to replace sine squared of x with 1 minus cosine squared x. Then I used u being the cosine of x to substitute here, so I get 1 minus, instead of cosine squared, I get u squared, the whole thing cubed. Cosine squared here, you got u squared, and I forgot that should be du, negative du, so let me fix that. I don't know why I wrote that down. So that should be negative du, and that's because of the negative sign, the derivative of the cosine being negative the sine. So all you have to do is multiply the thing out. You get a polynomial, which then you could do the polynomial integration. Once you've integrated the polynomials, then you would substitute back in. For u, you'd put in cosine of x. Okay, so that's it for today. I'm not going to assign any homework from this until Thursday. So